Okay, so here's the video for J-11, and these exercises, you might not see the point right now, but these exercises are going to build up to the limit definition of a definite integral, which gives us the exact area under the curve. And now the limit definition of an integral, this is called a definite integral. Sometimes they just say integral. And we're not going to have to compute the limit, but we need to be able to, in the future, in the next phase, recognize the limit definition. So we're going to do this. You're given a Riemann sum and its corresponding picture. Okay, so here's the Riemann sum. This is the corresponding picture. So this sum here calculates this estimation of the area under the curve from 5 to 7. And this estimation is being done by doing two right-hand rectangles. Okay, so we're going to use the picture to find delta x for each sum. And then we're going to write out the individual terms of the Riemann sum and then evaluate it. Okay, and then I'll make it more clear next phase where this sum comes from, where the input on this sum comes from. Okay, and a Riemann sum is just a sum of rectangles. All right, so basically right now I'm just trying to show you how this particular notation works. Okay, so alrighty. So right now, so the way that you get delta x is we're gonna go 7 minus 5. All right, so 7 minus 5, that gives us the length of the interval. So this is like A and that's like B. And maybe I should just give you like a formula for it. So delta x is always going to be B minus A over N. So B minus A and B are the endpoints of the interval. N is the number of rectangles. So it's 7 minus 5 over 2. So 2 over 2 is delta x. And guys, you could see delta x actually from, so every time we're looking for a pattern, every time you're going to see delta x like right here and right here. And I never simplified delta x because I wanted you to be able to see it like that. Okay. Now, what this thing here, okay, inside this sigma, all right, this is sigma notation and this is like the input of it, and I'll show you how to use it in a minute. But what this represents is the area of these rectangles, okay? And yeah, just try to follow as best you can and it'll come together tomorrow. But so what we actually have here every time is the graph of x squared minus 1. All right, and the area of this rectangle here is the height times the base, or the base times the height, but they always are writing it height times base. And the height is given by just plugging this right endpoint into this function. So the height is f of, I call that x sub 1, f of x sub 1 times the base. And now the base of the rectangle is always delta x. So when you're finding delta x, here you're finding the bases of those rectangles. And okay, but another way of representing delta or x sub 1 using delta x is we're just adding delta x to 5. Okay, so that's the starting point. If you add delta x to it, that's the length of this interval, then you end up at this right endpoint. Okay, so now if the stuff that I've said so far is a little bit unclear, this is the important part. So the important part is how this notation works. So if you look at this in here, it's very complicated looking, but what we want to do is we're going to plug, so this is telling us to take the sum of terms of this form from k equals 1 up to k equals 2. So we're taking, so this sigma means sum, so we're taking the sum of these terms starting with k as 1 and ending with k as 2. So the first term is going to go like this. I'm just going to write this, I'm going to write this term, and then I'm going to put a 1 in for k. So it is going to be 5 plus 1 times 2 over 2 squared minus 1. And then I'm multiplying that whole thing by 2 over 2. All right, so that is the first term of this sum. In the terms of a sum, you're adding them, so I'm putting a plus sign. Now I need the second term of this sum. For the second term, we're plugging in k is 2. So it's going to look the same, but 2 is going in for k. Okay. Now this sum is really not too bad because 2 over 2, that's just 1. All right, 2 over 2 is just 1. So the first term of this sum is, so that's 6 squared minus 1. Yeah, I'll just write that. So 6 squared minus 1, and then this is 7 squared minus 1. So this ends up being 35 plus 48. And I did actually already work this out. So this is 83. All right, and we're going to connect this formula to this picture even stronger tomorrow. But basically 35 is the area of this first rectangle, 48 is the area of that second rectangle. And so the area of the two rectangles together is 83. I'm going to do another one, and then you're going to do 2 just for practice, so that you can just really get to see how this notation works. Okay, now we're going to do this one. So first, let's find delta x. And remember, delta x is the length of each subinterval. So delta x, so it's b minus a, so 7 minus 5, over n, which is the number of rectangles, and this time it's 3 rectangles. So this time delta x is 2/3. Okay, and for now we're just making so we're just noticing that this delta x is showing up in the terms of this sum right here and right here. Okay, and now, so this time we have 3 rectangles. So we're going to have 3 terms to this sum. Okay, each term is going to be of this form. For the first term, k will be 1, all the way up to 3. So for the second term, k will be 2, and then for the last term, k will be 3. Okay, so for the first term of your sum, k is always this bottom number, and then for the last term, it's the top number. And then for the terms in between, it's whatever numbers are in between here. Okay, so first term is 5 plus 1 times 2/3 squared minus 1 times 2/3. That's the first term. Plus the second term, 2 is going to go in for k. 5 plus 2 times 2/3 squared minus 1 times 2/3. That's the second term of this sum. Plus 5 plus, this is the third and last term, 2/3 squared minus 1 times 2/3. Okay, now we have to add up all of those, add up those 3 numbers. Now this first term is going to give us the area of the first rectangle. The second term gives us the area of the second, and then the third term gives us the area of the third, and I will connect for you better on the next phase how that works. Now, this is kind of a lot to be plugging in to the calculator. Yeah, I think maybe we should just do it. I was going to show you a calculator way of a little bit faster of a calculator way. I wonder if I should. Yeah, I think that no, I won't. Okay. So we'll just plug this in. All right, be very, very careful with your parentheses, okay? So parentheses, 5 plus, all right, 1 times 2/3, you know, I'll use alpha y equals, is just 2/3. Now I'm closing parentheses, I'm squaring that, I'm subtracting 1. I'm closing that first parentheses, and then times 2/3. Okay, and actually, you know what? I'll just do the whole thing right now. Instead of hitting enter, I'll just do the whole thing. So now I'm going to do this plus sign. So plus this plus sign. All right, I'm opening up 2 parentheses. 5 plus 2. 2 times 2/3 is 4/3. I guess I'll just go 4/4, and then you square that, and then you subtract 1, and then you multiply that by 2/3. Whoopsie. 2/3. All right, and now this plus sign, plus, double parentheses there, 5 plus 3, no, that's going to be 6/3, so that's just 2. Yeah, because that's 6/3, so that's 5 plus 2, 7, squared minus 1 times 2/3. Okay. Yep, that's the same thing I got when I did like a little shortcut earlier. Oh, but over 28. 21, 28. Okay, yeah, I think that's right. Okay, so this is 20, 21, 28 divided by 27. I'll get a decimal. Okay, 78.815. Alrighty, and then, all right, so this is equal to 78.815. Okay, guys, so I'm just asking you to do 2 of these on the practice. So it's the same, the terms of the sum are going to be the same every time. It's just like the terms themselves are going to have like the same formula, but you guys are going to do one with 4. So I did one with 2 terms, 2 rectangles. I did one of these with 3 terms, which corresponds to 3 rectangles. Now you're going to do one with 4 terms and then 5 terms, okay? And then hopefully that will just give you a feel for how this type of notation works. And then tomorrow we'll connect this notation better to where we'll see where this notation comes from with regard to this picture.